Find the range of values of a for which this inequation will have at least one negative solution. One negative solution means one negative value of x. Let y be equal to 3 power x. If so, we have to solve y squared minus but y positive. Now this is a concave upward parabola, and know how to proceed. At least one negative solution if x is negative, what is the range of values of y? 0 to 1. At least one negative solution in x implies at least one negative solution in x implies at least one solution in y belonging to 0 to 1. Y is 3 power x. Suppose x is negative. This is the graph of y equal to 3 power x. For all negative values of x, the value of 3 power x is fractional, positive fraction. So, if x is some negative number, then y will be some positive fractional number. So at least one negative solution in x implies at least one solution in y belonging to the interval 0 to 1. Now this is concave upward parabola. And this inequation must become less than or equal to 0 for at least one value of y in the interval 0 to 1. So what are all the possible cases? You can have no real roots in the interval 0 to 1, or the limiting case 0 and 1 by themselves, or 1 is a root, something like that. Can it be?
Even if one root is between 0 to 1, you will have values?
No, this is case 1. There are different cases. One case is that both the roots beyond 0 to 1 or roots may be at 0 or 1. Right. The second case is exactly one root in the interval 0 to 1, like this. Or like this. Exactly one real root in the interval 0 to 1. If it is so, then for these, if you take this parabola, for these values of y, the expression is negative. we should have at least one value of y in the interval 0 to 1 for which the expression is negative. If so, there are three cases: either both the roots are outside the interval 0 to 1 root inside the interval, or both the roots inside the interval. This is also okay, because the expression can be 0 also. So find the values of the parameter a such that this expression behaves in this manner, similarly here and here. Then take the union. Either of these is okay for the expression to become negative. So if the expression has to become less than or equal to 0 in this manner, for y in the interval 0 to 1, f of 0 times f of 1, both f of 0 negative, f of 1 negative. Okay, this is the case of, you have, this is the case of what? K1, K2 lying in the interval of the roots. So you should write many conditions. What are all the conditions? Okay, f of K1 negative, f of K2 negative, f of K1 negative, f of K2 a times, okay, here already concave upwards, f of K2 negative, then yes, that's all.
So our instead we can take cases where both roots are back from
Yes, yes. Whichsoever is convenient, you can do. For this, f of K1 negative, f of K2 negative are the only two conditions. K1 inside the interval of roots, K2 also inside the interval of roots. Then, okay, f of 0, what do you get? F of 0 negative implies a, then f of 1 negative, you get a greater than 2. Of course, here we have equality also. F of 0 can be 0, f of 1 can also be 0. So we will include those cases. So what is the overall solution here? A greater than or equal to 3. We have to take the intersection because both should happen simultaneously. Now in this case, one root lying between 0 and 1. Exactly one root between 0 and 1. Therefore, f of 0. No. Or f of 0 and f of 1 are of is that sufficient? F of 0 and f of 1 or of opposite side, then one root has to be in between 0 and 1. Equality when this by itself intersects either 0 or 1. Here, when you take, okay, f of 1 0, f of 1 is 0, but f of 0 can be either 0 or negative. It is not positive. If it is positive, then it comes under this case. But anyway, somehow we have to count that also, so no problem. You understand what I am telling? This by itself actually takes care of something like this. A root, f of 1 0 and another root here. Now f of 0 negative. Yes. Anyway, we are interested only in y greater than 0, right? That's okay. Y equal to 0 is not in our domain. Okay, y positive only, but we can have a graph bubbled here, that is, that point is excluded, but it starts from here. That's what we say f of 0 being 0. That we will get that particular graph. Anyway, f of 0 times f of 1 negative implies what do you get? A belongs to 2 to 3. When this becomes 0 or whatever, or it doesn't, anyway it will be taken care of in one of the cases. Here both the roots in the interval 0 to 1. So we have to start from discriminant greater than or equal to 0, for which discriminant greater than or equal to 0, what do you get? Then you have to say f of 0 times f of 0 f of 1 positive, and the vertex should, the y coordinate of vertex must be in the interval 0 to 1. If you stipulate all these conditions, I think there will not be any solution. You check. If all these three conditions should hold good simultaneously, no value of A. Okay, here we are missing A equal to 2 then. So okay, we'll take the equality. So what is the union of these two? Union of these two? Okay, can here we just depend on that whether the equality is valid. A equal to 2, what will happen if A equal to 2? Just check. Y square minus 2y. Okay, how will this graph be? Y square minus 2y plus 1. So it will be like this. Right. So nowhere in the interval 0 to 1, 1 not included, in the interval 0 open interval, the expression must become either negative or 0, but it becomes 0 at the right extreme. What we want is the expression becoming less than or equal to 0 in the interval y belonging to open interval 0 to 1. But if you take a as 2, what is happening? If you take a as 2, therefore the intersection of this will be strictly a greater than 2. So if a is greater than 2, the expression becomes less than or equal to 0 for at least one value of y in the open interval 0 to 1, and hence we can say back in x. For at least one negative value of x, this expression in x is less than or equal to 0. Okay, next case, at least one positive solution in x implies at least one solution in y belonging to, at least one solution in y belonging to, when x is positive, y is, consider the graph 3 power x, this is x. When x is positive, y is greater than 1. So at least one positive value of x means at least one value of y in the interval 1 to infinity. Again, concave upward parabola becoming negative for at least one value of y the expression becoming negative somewhere in this region. So it can be like this. Expression becoming negative at least once in this region. That means one root beyond 1. If both the roots are to the left of 1, it is not possible. In this case, exactly one root to the right of 1. The other case is both the roots of course boundary case we have to consider. That finally we will see how it is. That is, one lies in between the roots. So f of 1 negative implies a greater than 2. In this case, we should have f of 1 positive and then discriminant must be greater than 0. Both the roots to the right of 1. So first you should write d greater than 0. Two real roots exist because f of 1 greater than 0 is okay for even this case. So d greater than 0, f of 1 greater than 0, and then that y coordinate of vertex is beyond 1. These are the three conditions. If you apply, you will get no solution. And check the boundary condition. If a equal to 2, that's what we already seen. If a equal to 2, what will happen? Exactly at? But we want this expression to become negative beyond 1. So a equal to 2 doesn't yield that. Therefore the solution is a greater than 2. So what does that mean? When a is greater than 2, there will be at least one solution, one negative solution for x and one positive solution for x. That is, in y there will be one solution in the interval 0 to 1 and another solution in the interval 1 to infinity, a greater than 2. At least one solution in the interval 1 to 2 for x. So what can you say for y? So the expression must become less than or equal to 0 at least once in this interval. So it can be like this or no roots in the interval 3 to 9, one root in the interval 3 to 9, two roots. You can classify the three the three cases. You know what to apply: f of 3 negative, f of 9 negative, and then finally check the boundary cases as well. Okay, if you want to include the boundary case here. Oh, sorry. Okay, for this, here f of 3 times f of 9 negative implies, check whether you get these results. So the union of these two finally will be a greater than 3. What happens when a is equal to 3? Check the boundary condition. Once you check the boundary condition, then settle with this a greater than 3. Last subdivision, at least one real solution. At least one real solution means either x greater than 0 or x less than 0 or x equal to 0. For solution in x greater than 0 you have solved. For solution in x less than 0 you have solved. Both cases you got a greater than 2 as the solution. Then you have to solve for x equal to 0. If x equal to 0, you get the solution a greater than or equal to 2. Put x equal to 0. You will get a greater than or equal to 2. Okay. So combining all the cases, the solution will be a greater than or equal to 2 itself. So a greater than or equal to 2 ensures that there is at least one real solution.